Hello, we are here together to try to understand the magnetic field created by a solenoid. A solenoid is a helical coil of wire where a current of electron will flow in it and create a magnetic field. We'll try to simulate the ions or charged particle with SIMION. I invite you to subscribe to my channel because I will publish several videos on that topic. Let's begin with a small reminder. Electric and magnetic forces arise from the same phenomenon, the electric charge. In fact, the electric field of a charge gets distorted when it starts moving and a new force appears, the magnetic force. Magnetic force involves particles in movement and it's just a consequence of special relativity. I recommend you to check the really nice video from Scientific Click to better understand these concepts. They did a terrific job with illustration and explanations. The big difference between electric and magnetic field is that in a magnetic field, a stationary charged particle does not feel any force. In contrary, a moving particle experiences a force, and the intensity of this force is directional and depends on how perpendicularly the particle moves. This will tend to create circular trajectories. And what I really want to highlight in this introduction is that even if electric and magnetic fields are linked, trajectories of the ions will be really different. For instance, trajectories are mass-dependent in static magnetic fields, whereas trajectories are mass-independent in electrostatic fields. To generate a magnetic field in SIMION, you can draw a potential array that will generate a magnetic potential. SIMION defines magnetic potential in mags, which are to be Gauss time grid units. For instance, you can draw two pole magnets, set one pole to 3000 max and the other one to 0 max. So in this simulation, I define three groups of particles with different masses and energies. The red one have a mass of 200 and energy of 1000 electron volt. The blue particles have a mass of 200 but an energy of 2000 electron volt, and the green one have a mass of 2000 and an energy of 1000 electron volt. I'll let you understand the different trajectories they have, and if I fast adjust the potential to 200 and run the simulation, you can see that the magnetic field is less strong. You can also record data, for instance the final energy at the ion splat. You can see that the final kinetic energy is the same. So we change the trajectories and the focus of the ions, but not their energy. Keep also in mind that magnetic potentials are not as simple as electrostatic ones. If all points of an electrode have the same electrostatic potential, is it not so obvious for magnetic potentials? Electric fields can be shielded, but not magnetic fields. As I said, magnetic fields arise from moving charged particles. So in our life, most of the magnetic fields are generated by currents flowing through wires. If the current is constant, it creates a constant magnetic field that can be calculated with the Biot-Savart law. This law calculates the magnetic flux density by integrating the infinitesimal small contributions dl of the wire. Therefore, adding all the dl contributions, you will end up with the total magnetic flux in a point. If you have some coils in your wire, you create a magnetic field uniform inside of it. The law gets really easier to integrate for coils, and you can even have an approximation for long solenoid. At the end, we have an electromagnet with a north pole and a south pole for which the magnetic field can be calculated with the Biot-Savart law. The integration of this law in each point of space is quite well optimized in SIMION. To create a solenoid in SIMION, you need to use a user program, because in the Workbench user program, you can load the integration support of the law called SIMION XM field. Then you can define your solenoid. By that I mean define all the parameters that will impact your magnetic field. So the current, the position, here defined by the beginning position of the solenoid by minus 50x00, and the end position of the solenoid 50x00. Then the radius and the number of loop. Finally, the magnetic field in the PA is calculated in space using the segment M field adjust. In the other action segment, I will try to add a color to my ions in function of the magnitude of the field. When the ions are in a region below 3 Gauss, the color will be black. Above 9 Gauss, the color will be green. And finally, the color will be red when they are between 3 and 9 Gauss. Now I can fly the ions. With the integration function support of SIMION, you don't create a solid solenoid. It is just overriding the magnetic field in the PA instances, so you cannot materially visualize your solenoid, but the magnetic field will be simulated. In a way, that's really interesting because unlike electrostatic electrodes, magnetic poles do not have a totally uniform magnetic potential across the surface. The color adjusts a visual effect. My beam is not ions, but electrons having an initial kinetic energy of 1 electron volt and a cone direction. First thing to observe is that some electrons are repelled because they have a starting angle too large for the radius of my solenoid. I define a solenoid of 100 turns with a radius of 10 mm. It should be something like this with more turns. Second thing to observe is the circular trajectories inside the uniform magnetic field. Remember that trajectories are mass dependent, so if I change the mass to some few units, I will change the trajectories. This is really great because in this case, for example, the trajectories are not affected. So you can imagine and design an instrument where electron will be affected by a small magnetic field, but the ions with higher mass will not move at all. Then if I give an initial energy of 0 electron volt to my electrons, they will never start flying because remember, magnetic field applies only on moving particles. What happens if I change the number of turns to 50? The magnetic field inside the solenoid decreases because it is proportional to the number of turns. If I change the current, we will have the similar effect. The magnetic field will decrease. You can also increase or reduce the radius to avoid repel electrons. For example, here in this case, I can increase the radius so that all my electrons will enter the solenoid. So you can really play on all the parameters here. Last thing I would like to mention with you today is the focusing. It is hard to understand why a uniform magnetic field provides focusing, but remember that my charged particles enter with an angle and they will feel a force given by the Lorentz formula. The particles are moving with a velocity v, which has a component v perpendicular and v parallel to the magnetic field. So the path of the particles will be a spiral. However, to fully describe this spiral and focusing that is sometimes occurring, you may to invoke some theorem and concepts and play with geometry. If you want to go so far, I invite you to read this article to really try to understand and describe the entire movement of the particles inside the spiral. Okay, it's time for me to conclude this video, and I just want to make a take-home message taking into account all the conclusions we have learned today. And the first thing is that a solenoid acts as an electromagnet with a uniform magnetic field inside. Then stationary particle doesn't fly. This is really important because remember that magnetic and electric fields arise from the same thing, so they arise from the electrical charge. But a magnetic field is linked to particles in movement and is a consequence of special relativity. Then trajectories are mass dependent. This is also really important if, for example, in many instruments we use the fact that particles with different mass will behave differently in a same magnetic field. Then magnetic force doesn't change the kinetic energy of the particles. And finally, magnetic fields cannot be shielded as electrical field, and poles don't have a uniform field across them. Don't forget to subscribe, especially if you are interested in SIMION's simulation, because I've already published 2 of them, one about Itzel lens and understand the focusing. It was my first video on YouTube, so maybe it's a bit rubbish, but at least you can understand how it works. And then the second one is about importing STL file from SolidWorks or any kind of software into SIMION and simulate the fly of the ions. So subscribe for that.